Copper has a speed limit, not how fast the electricity moves, but how far it can carry a signal before it smears into noise. At the speed AI chips now talk to each other, that distance is down to about 1 meter. Not one building, not one room, 1 meter, not even top to bottom of a single rack, which is why the wires are quietly being swapped for light. Rewind a few chip generations. A copper cable could carry a chip signal about 3 meters. Then the signaling got faster and copper's reach collapsed, past 2 meters, then down to roughly 1. The faster the data, the shorter the wire. The moment a signal leaves one chip to reach another, it runs into something older and more stubborn than any transistor, the physics of a wire. And that physics just quietly broke the thing the entire AI build-out is bolted together with, copper. Here's exactly how a wire dies. Start with what a fast signal actually is. Not a smooth wave, a frantic on-off, billions of times a second. Modern links squeeze in more by using 4 voltage levels instead of 2. It's called PAM4, so each moment carries 2 bits instead of 1. Even a generation back, at 112 gig PAM4, the core frequency of that signal already sat near 28 gigahertz. Now the copper fights back. At those frequencies, the current stops flowing through the whole wire and crowds onto its outer skin, the skin effect. So the wire behaves thinner than it is, its resistance climbs, and the faster you push, the more the copper bleeds the signal away as heat. Roughly speaking, the losses double every generation. And here's where smears into noise stops being a metaphor. As the signal weakens over distance, each pulse spreads and starts overlapping the pulse behind it. The clean 4 levels blur together. The receiver can no longer tell a 1 from a 0. The bits literally smear into each other. Engineers call it inter-symbol interference. You can just call it the wire forgetting what it was carrying. That's why the number is a distance, not a speed. At 224 gigabits per lane, a passive copper cable holds a clean signal for about 1 meter. And the thing killing it isn't power, it's insertion loss, the signal simply fading out. A rack is 2 meters tall. The wire can't reach top to bottom of the box it lives in. So the first move is to prop the wire up. Put tiny chips inside the cable ends that clean and redrive the signal, active copper. You stretch the reach back to 2, maybe 2.5 meters. It buys a generation. It does not buy a building, which leaves a gap. Copper can do the short hops inside a rack. Real distance needs light. In between sits a dead zone the whole industry is fighting over. But before you write copper off, look at what it spends. A passive copper cable burns essentially 0 watts. No lasers, no chips, no power, just metal. That's copper's superpower, and it's why this story isn't as simple as light wins. Copper isn't being pushed out because it's wasteful. It is the most efficient link there is. It's being pushed out because it can't reach. Light reaches. A glass fiber carries a signal across a data center hall without breaking a sweat. So why didn't AI just use light everywhere from the start? Because until now, light lost on watts. To To put a signal onto a fiber, you convert electrical to optical, and the classic way, a pluggable module on the front of the switch, is thirsty. A single 800 gigabit module burns around 15 watts, roughly 19 picojoules per bit, much of it wasted shoving the signal across lossy board traces. That sounds small until you multiply. One AI cluster, 200,000 GPUs, draws about 435 megawatts. Of that, around 17 megawatts is nothing but the optical transceivers. 17 megawatts just to turn electricity into light and back. The fix is simple to state. Stop shoving the signal across the board. Move the optics onto the same package as the switch chip, co-packaged optics. So the conversion happens millimeters from the silicon instead of centimeters. Meta measured it. The same 800 gigabit link that cost 15 watts as a pluggable dropped to about 5.4 watts co-packaged, a 65% cut. Running 1 million port hours with 0 link flaps, Broadcom's version does 6 to 7 picojoules a bit, a third of the old number. And this is what makes it a now story, not a someday story. As of 2026, this is shipping. A leading foundry's co-packaged optics platform went into mass production in the spring. The first photonic switches arrived early in the year. A 102 terabit switch, codenamed Davison, has shipped since late 2025, both built on that platform, both claiming 3.5 times the power efficiency of the pluggables they replace. The optics moved onto the show floor. The transition stopped being a slide and became a product. Now the honest part, because a wrong sense of scale is its own kind of lie. Networking is only about 9% of a cluster's total power. Swap every switch to co-packaged optics across a 3-layer network, and you save on the order of 2% of the whole facility. Today, co-packaged optics is maybe 0.5% of the optical modules in AI data centers. The forecast is 35% by 2030, but not yet. So copper is not dead. It keeps the last meter, every short in-rack sub-meter link, precisely because it burns nothing. The vast majority of the longer rack-to-rack links are going optical, and the money follows. An 800 gig module runs on the order of $400, a 1.6 terabit part closer to $1,400. And when a single buyer orders 2 million of them, that's a $3 billion line item just for the privilege of moving light. Copper and glass are splitting the machine between them by the meter. Step back, and it's the same shape we keep finding. Every year, the chips got faster. Every year, the wire got shorter. The bottleneck was never the math. It was the distance the answer had to travel to get out. Copper hit a wall you can measure with a ruler, 1 meter. And the fix isn't a faster wire. It's no wire at all. Not compute, delivery. Because this is what the whole build-out keeps running into. Every layer of this machine hides a wall like this one, a piece of physics quietly deciding what the software above it is allowed to do. A wire that got too short, a watt that has to leave as heat, a queue that takes years. The chips get the headlines, the walls decide the winners. We keep going one layer down until we find the next one. It's right here.